Hello, my name is Rui Cardoso. I'm Senior Lecturer at Brunel University London, UK, and I'm going to deliver a short course on numerical methods for structural analysis. We will start with the weighted residuals, and then the final goal is to get into the finite element method, which is the most common used method in structural analysis. Before I start, I would like to give this information. So I recently published this book, Stress Analysis for Lightweight Structures, a MATLAB-oriented approach. This book includes, so it is a 700 pages book. It includes many introductory chapters, but the chapters we are going to focus in this short course is going to be numerical methods, basically this chapter 10 and also chapter 11. So like I said, we will start with the weighted residuals method. Okay, we'll talk about Galerkin's method, collocation method, and then we will move to weak formulations, which is very important to derive the finite element matrices for elasticity. And then we will, in this section 10.4, we will derive some important formulations for some specific elements, for 1D elements, 2D and 3D elements. In chapter 11, we'll focus more on plate and shell elements. Okay? So in this short course, so these are some figures I took from my book. So you will be able to model this kind of structural components. For example, an hinge. Okay. So you have MATLAB scripts to get the finite element matrices for the 3D elements, brick elements. That is included in the book. So you can predict the equivalent von Mises stress. So the pin here is modeled as a rigid body, but then the other two parts of the hinge, they are deformable bodies, and you can see the distribution of the von Mises stress. You can also see the distribution of displacements or wherever else you want to see. Also in the book, in the chapter for plates and shells, you will you have basically the MATLAB routines to build the shell elements, and if you want to implement that in your MATLAB code, you can get results similar with these ones. For example, this one with a cylindrical shell with a concentrated force, so you get the deforming configuration, something like this. So this is something you can predict with the MATLAB scripts in the book. So another type of things you can do from the book is a buckling analysis, getting the buckling modes for a plate element, in this case with some symmetric boundary conditions. You can get different buckling modes and predict the structural behavior of these structural elements under compressive or in-plane shear loading. Okay. So what we are going to learn in this short course is basically the weighted residuals and finite element method. So with the weighted residuals is the foundation to get the finite elements that allow to do this kind of problems, analysis of this kind of problems. So I hope this short course is valuable to you. So yeah, that's it. Hello. Let's continue our course on numerical methods. So today what I propose to do is to introduce a quadrilateral finite element with 4 nodes, and then to use the developments we did in the last session for the weak formulation for elasticity, and derive the strain displacement matrix for this element and apply it for a plane stress example, okay? So we'll see how to build the stiffness matrix of each element and on how to assemble the contribution of all elements for the global stiffness matrix of the system. Okay, so we will have a quadrilateral element, which I'm going to represent here in the physical space, and this element will have 4 nodes at the corners of the quadrilateral, something like this, okay? So typically these nodes, they are numbered in a clockwise direction. So if you clockwise like this, you will number nodes like this: 1, 2, 3, 4, right? So we are going to see this is in order to get a positive Jacobian, but anyway, something we'll talk later. Let me delete this. So a quadrilateral element will be something like this. So if you want to use it in plane stress, you will have the element in plane like this, okay? So nodes 1, 2, 3, 4, and then each node will have a degree of freedom. So this is something you are going to start listening now. For a plane stress element, those degrees of freedom, so if this is my, if this is my x and y axis, each node will have a degree of freedom which is going to be the displacement of node 1, in this case, in the x direction, the displacement of node 1 in the y direction, which we represent with the letter v, and same thing for all other nodes. So u2, v2, u3, v3, u4, v4, okay? And of course this element will have some dimensions in the x and y direction, okay? So I will represent here. So it will have a dimension, let's say Lx, and it will have a dimension Ly. Okay, so these degrees of freedom that you see there, so this element will have approximation functions or shape functions. And for example, imagine you want to get, so I'm going to represent in blue, you want to get, for example, the coordinate of this point here, okay, in the element. So what you'll do is, so let's say you want to get the x and y of this point. So what you do is, for example, for the x, you do summation of the shape functions of the element times the nodal coordinates of the point. So I can expand this, because we have 4 elements, we will have shape function number 1 times the x coordinate of node number 1 plus n2 times x coordinate of node number 2 plus n3 times x3 plus n4 times x4. Same thing for the y coordinate. We interpolate using the shape functions and the coordinates at the nodes. So n1 y1 plus n2 y2 plus n3 y3 plus n4 y4. Okay. Now, the isoparametric finite element, what it does basically is to, so I can move this a little bit up like this. So the isoparametric concept, what it does is, so what we have seen so far, we interpolated the geometry, right? So if we want to get the coordinates of any point inside the element, we use the shape functions and the nodal coordinates. But the isoparametric concept is we can also interpolate the displacement field, u and v. So in this case, we use the same shape functions that we used before, and we need to use the displacements at the nodes, or the degrees of freedom at nodes. For the displacement in the x direction, those degrees of freedom are going to be u1, u2, u3, u4. And for the vertical displacement, we use the same shape functions, but now we use the vertical displacements at nodes, or the vertical degrees of freedom at the nodes, right? So this is the isoparametric concept. So maybe I can write here. In fact, the wording says everything. I think so. If you put isoparametric elements, okay. The word isoparametric says everything, because iso means we are using the same approximation functions, okay, for interpolating the geometry and interpolating the field or interpolate the degrees of freedom, the field that are defined at the nodes. Okay, so these are isoparametric elements and are the most widely used in any finite element software package. Okay, so you also see some familiarity here with what we did for the weighted residuals in the first sections of this course on numerical methods, when we built the approximation function. Remember, we built an approximation function, something like this: summation of shape functions times unknown coefficients at so we define these approximation functions as we do for the finite elements. We are going to see for this quadrilateral element with 4 nodes what are the shape functions we are going to use. So we define a priori these shape functions, and then we replace the approximation function on our differential equation, remember, and then we solve the solution for these unknown parameters A. This is what we did in the past sessions. So now in the finite element method, you can see a very strong correspondence between the unknown constants A and the degrees of freedom, right? So in our case, in finite element analysis, our unknowns A are going to be the degrees of freedom at the nodes of the element. And you also see a very strong correspondence between the shape functions and approximation functions, right? So in fact, we are here doing an approximation as well, and our domain in this case is this finite element with 4 nodes, right? Okay. Okay, so let me copy maybe this figure here. Copy, and let me put it here in this new page. Okay. Now, before we continue, there is another important point that I need to discuss with you, which is, as you can see, we defined for this element, we defined some dimensions for the element. So when you do a mesh, this in the domain, so the mesh will create many finite elements, right? And each of these elements will have a specific dimensions, right? Lx and Ly. The problem here is because we will be doing many different examples when we use a finite element package, software package, and we need to, when we are coding these packages, these finite element softwares, when we are programming, we cannot, for for any reason, guess what are going to be the dimensions of these elements. So this is quite a difficult thing to do, to implement, to program. So what we have to do is and the way the things are done is we need to map these physical coordinates into a coordinate system where our dimensions are fixed for the elements, always fixed. So then, independent of the problem you are solving, the computer or the programming will always program the shape functions for this element in a fixed dimensions framework, if you want, or coordinate system. And we can only do this one time, and then it will work for any example with the different physical dimensions. So that's what I want to introduce now here. So we can say this is a physical domain for the element. And I'm going now to create here so the same element with the same 4 nodes. So this physical domain is given by the xy coordinates, right? Now here I will have again node 1, 2, 3, and 4, and I will call this the natural domain. Some authors, they call this the parametric domain. You can put here parametric. Okay, and the good thing about this domain is that we'll have at the center of the element our coordinate system, which commonly is called by these Greek letters xi and eta, and this distance from here to here is -1. From here to here is +1. So this is in the xi direction. For the eta direction, this distance from here to here is +1, while from here to here is -1. Okay? So in this natural domain, the element will always have these dimensions, -1. So if you want, you can say the coordinates of node 1 are going to be in this coordinate system xi eta -1, -1. Node 2 is going to be +1, -1. Node 3 is going to be +1, +1. And node 4, the coordinates are going to be -1, +1. Okay? So in this natural domain, this element will always have these fixed coordinates, -1, +1, -1, in this natural coordinate system, xi eta, right? So we can say that the coordinate axis for this natural domain is going to be this xi eta, okay? And now what we are going to do next is we are going to build the shape functions on this natural domain, natural coordinate system, okay? That's what I'm going to do next. Okay, so I have to repeat this bit again, so sorry, because there happened some problem with this video recording on the app here. It didn't record the last bit I did, so I have to repeat everything again. So what you are seeing here on screen is basically the 4 shape functions for this quadrilateral element with 4 nodes, okay? These are the standard shape functions that are defined for this element. So these shape functions, they were defined with some important properties. For example, if you are, imagine you want to interpolate at point 1. Okay, so you know that at point 1, so I'm going to try to do here in blue, at node 1, you have the coordinates xi equal to minus 1 and eta equal to minus 1. So if you replace in these shape functions, you get n1 equal to, you will have here, if you replace xi by minus 1, you will get 1 plus 1 makes 2. Same thing here, 1 plus 1 makes 2. So 2 times 2 is 4, 4 over 4 makes 1. And then you get, for n2, look, if you replace here xi by minus 1, you get 0. 0 times anything else is going to be 0. So n2 is going to be equal to 0. If you replace again in n3 xi by minus 1, you will get 1 minus 1 becomes 0. So it delivers n3 equal to 0. And for the fourth shape function, if you replace here eta by minus 1, right? Eta by minus 1, you get n4 equal to 0. And then if you look at this, the conclusion is, for node 1, shape function n1 is equal to 1, and all other remaining shape functions, n2, n3, and 4, they are all equal to 0. If you are at node 3, for example, what is going to happen, and you can do the calculations yourself, so I'm going to speed up a little bit. You get n1 equal to 0, n2 equal to 0, n3 equal to 1, n4 equal to 0. And if you go to node 4, you get n4 equal to 1 and all other equal to 0s. At node 2, n2 equal to 1, all the other remaining shape functions equal to 0. So in both cases, if you notice, if you add all these shape functions together, yeah, the result is always going to be equal to 1. And this is the partition of unity, which is a very, partition of unity is a very important property for the definition of the finite elements and the shape functions, okay? So these are the shape functions we are going to work for this element. So they are, so these polynomials that you have in these shape functions, they are bilinear polynomials, or bilinear polynomials, sorry. Because if you do these multiplications, you will have terms that will depend on xi, will depend on eta, and will depend on the product xi times eta. So that's why you have, we call these bilinear shape functions, okay? There are other type of quadrilateral elements with more nodes. There are, for example, quadrilateral elements with 8 nodes, where you have additional 4 nodes at the mid edges of the element, so it makes a total of 8 nodes. So you will need 8 shape functions, and in this case you will have defined quadratic shape functions. You also can also have quadrilateral elements with 9 nodes, including a node in the center of the element, and then you need 9 shape functions, all right? So I'm going to stop here to see if I didn't have trouble in recording this bit of the session. I will come back. Okay, seems all good. So let's continue. So I'm going to copy this to a new page. Let me just maybe get rid of this green stuff here, because we have already the coordinates xi and eta at nodes, right? Okay, so this is our quadrilateral element with 4 nodes in the natural coordinate system, xi eta. Of course, we will also have the physical domain. So what I'm going to try to do now with you is to to build the mapping between the physical and the natural domains of this element. So in order to do that, you need to realize that at the end we will need to do an integral. Yeah, so you learned that from the previous sessions. We need to do an integral in the domain, in our domain. So when we are working with one finite element, our domain is going to be the domain of this, or the area of this element, right? So if you are doing for plane stress, if you want to consider the volume of this element, you just multiply the area by the thickness of this element, right? So our domain, so we will have to integrate something, okay, in the physical domain. That's we always have to integrate something in the physical domain. So this physical domain is given by this dx dy, where x and y are the global coordinate axes. Okay, so what we want to now do is find a way to say this is going to be equal. So basically, maybe I can be a bit more accurate. So this integral now is going to be a double integral, because we are integrating in an area, right? So this one is going to be along x, this one is going to be along y direction, right? So this is going to be our domain for a plane stress element. What I want to do now is to find a way to say that this integral in the physical domain, I want it to be equal to this integral here, with these boundaries very well defined in the natural domain, from -1 to +1, something here, and then I will integrate in my natural coordinates or parametric coordinates, xi and eta, right? So this here is something I can easily do in the computer, because the limits of my integrals do not change. It's always between -1 and +1. While this one here at the top is impossible to implement in the computer, because if you are doing different examples, it means you need to code different integrals, right? You need to integrate different integrals, because these dimensions in the x and y direction, they are changing. So this is a huge inconvenience. So that is the main goal, and this is why it is possible for these finite element softwares to work with any example you are doing. So this mapping is quite critical, and if you look carefully, the major thing that we need to do now is basically just to see how we can transform this infinitesimal dx and dy coordinates into these infinitesimal parametric coordinates. So if we know how to do that, then problem solved. Okay? Right, very good. So the first thing we are going to do is quite, in fact, an easy thing to do. So maybe so I'm struggling here a little bit with space. Let me just scale this down a little bit to see if it fits here. Yes, much better. So I will start with dx, maybe this black color, dx. So in order to have dx, I'm going to use the chain rule for derivation, which is quite a basic stuff. So I'm going to say an increment in x, or an infinitesimal x in the physical domain, is going to be given by the derivative of x in order to xi times an infinitesimal increment in the xi direction, plus the derivative of my x coordinate in order to eta times an infinitesimal increment in the eta direction. So this is the chain rule if you look carefully, right? Why am I doing this? Because look, these two terms are in fact quite easy to calculate. If you just look, maybe I can copy these shape functions to the next page to make it easier for us. Put it here and scale them down. Okay, something like this. So these are our shape functions for our element, quadrilateral element. And doing these derivatives is in fact quite easy, because we know from the isoparametric element that x is going to be equal to this summation from I equal to 1 to 4, because we have 4 nodes. Okay, x, y, they are known. So this x, y is the x coordinates of nodes 1, 2, 3, and 4. They are known because when you do a mesh in a finite element software, you know the coordinates of the nodes. You know where the nodes are located. And these coordinates of the nodes, they are fixed. Okay, when you do a mesh, the coordinates, the nodes are fixed in those positions. So this, when you derive x subscript I is going to be a constant, so that derivation is going to be equal to 0. But the same does not happen for the derivation of the shape function. So if you are doing now, for example, if you look at the dx d eta, this is going to be basically equal to summation of the derivatives of the shape functions in order to eta times xi, right? And the derivatives of shape functions in order to eta, they are quite easy to obtain, because we know shape functions here is in fact very, very easy to get these derivatives, and it's something we can do very quickly here. Just struggling with space. Maybe I can do something like this. Yeah, maybe something like this is fine. So the derivative of shape function number 1 in order to c, is going to be minus 1 over 4 1 minus eta, isn't it? Yeah? Does it make sense? The derivative of n2 in order to c is going to be equal to 1 over 4 1 minus eta. The derivative of n3 in order to c is going to be equal to 1 over 4 1 plus eta. And the derivative of n4 in order to c is going to be equal to minus 1 over 4 1 plus eta. Okay? So, very, very simple derivations. And basically what is going to happen is we have the derivative of we have this derivative here, right? Oops, sorry. This derivative done. Dx deta is a very similar procedure. Now the only difference is we are going to make the derivatives in order to eta instead of in order to c. So I have to derive the shape functions in order to eta. Let me see if I can, well, maybe I need to scale this down a little bit, see if everything fits. Move this a little bit more to the, so this can become a little bit organized. So the derivative of n1 in order to eta is going to be equal to minus 1 over 4 1 minus c, right? Derivative of n2 in order to eta is going to be equal to minus 1 over 4 1 plus c. 1 over 4, 1 plus xi, and derivative of n4 in order to eta is going to be equal to 1 over 4, 1 minus xi, right? So these are our derivatives. So I can say, so if I continue here below, I can say the following. I can say dx is going to be equal to summation equal to 1 to 4 b and I dxc times xi. This will multiply dxc plus, now I need to have the x derivative of x in order to theta, which is summation I equal to 1 to 4 derivative of ni in order to eta now, and this will multiply my d at eta, right? So the same thing can be done for if you are looking for the y direction. So you will have in this case the derivative, or if you want, before we go into this, you will have dy over dxc times an increment in xc plus dy over the eta times an increment in eta, right? So this y, the derivative of y in order to xc and derivative of y in order to eta, is done by using these derivatives we did here for shape functions, right? So at the end, and I'm speeding up a little bit here now, otherwise this on one side becomes too boring, and on the other side the video becomes too long, and I think you already got the message, I hope. So if you do that, you'll get at the end summation from 1 to 4, derivative of the shape functions in order to eta in this case. Now this will multiply the yi coordinate dxc plus, now the derivative, sorry, I did a mistake here. This is not in order to xc to eta, this is in order to xc. And now here is the derivative of shape function in order to eta times the coordinates y of at the nodes, which will multiply increment in the eta direction. Okay, so this is now very important. What we got. I'm just going to copy to a new page and go from there. So we are going to do a full example. So you might be thinking, okay, but the derivatives, this derivative in order to xc and this derivative of shape functions in order to eta, they still have xc and eta. But what we are going to do is we are going to do numerical integration, and then this xc and eta, they will be replaced by specific coordinates eta and xc, or xc and eta, in a particular points, which are the Gauss points or integration points. So at the end we will not have this xc and eta, but we will discuss that later, okay? So what I want now to show you, so let me paste this here, maybe shrink a little bit. So this important chain rule for the derivatives, if you look carefully, on the left hand side you have the physical coordinates or infinitesimal coordinates dx and dy, and on the right hand side you will have the natural coordinates dx, d eta. This is exactly what we are looking for. Don't forget that our starting point was to find a way of converting an integral in the physical domain into an integral in the natural domain so that it can be programmed in the computer, right? And that's exactly what we are achieving here. So I'm going to put in this form, which I think will be easier for you to see the relationship between these two. So on left hand side we have this, and then I can put in this matrix, I can put this first term. I don't know if you are seeing my selection. So this first one, which is this, okay. Now I'm going to put this one here in the first row, second column of this matrix. So I'm going just to copy paste. Okay. Now this is going to be on the second row, first column. Again, copy paste. And this last one is going to be on second row, second column. Copy paste. And then this matrix will then multiply the increments in the x direction and eta direction. So if you do the multiplication of this matrix with this vector, you get exactly what you have here in these two equations at the top. Okay? So, this matrix here that we define is called the Jacobian matrix. If you want, I can say Jacobian, which is a matrix that allows the mapping, if you want, between the natural coordinate system xi eta into the physical or global coordinate system x, y. Okay? And most importantly, this infinitesimal area element, so if you want, this is an area element in the physical domain, dx, dy, which we will need, we will need to solve this integral in the physical domain. It is obtained by calculating the determinant of the Jacobian and multiplying this by infinitesimal area. So I can put this infinitesimal area in the xy domain. This is the infinitesimal area in the xi eta or natural domain, right? And now the most important thing of all is, maybe I can copy these integrals here. Don't forget, this was our major aim. Can put it here. Basically, this integral is going to be equal not only to this, but, so if you want, we have something here, right? So dx dy is going to be equal to the determinant of Jacobian multiplying dxi d eta. And this is a very important point that we are going to use for our plane stress example, okay? So basically what I've done today, maybe I think this session can finish here. We still have one more session at least to solve our example for plane stress. But I would like to stop here because this is a very important concept and I want it to be very well understood. So we need to do an integral in the weighted residuals or in the weak formulations that we derived last session for when we derived the finite element matrices. We always need to do an integral in the physical domain, right? The challenge in the finite element analysis is that physical domain changes for every problem we are doing, okay? So if you are doing, for example, a plane stress example for a plate in tension with a plate, a quadrangular plate with 100 millimeters, then you will have some element size. But if you are still doing the same example, plane stress, but now the plate instead of 100 millimeters has 200 millimeters width and height, then the size of the element, if you keep the same number of elements, the size of the element will change. And how does the computer knows that? How does the finite element software knows that? It doesn't know that. So that's why we had to create this natural domain so that the computer always knows that is doing an integral for a domain that is always from -1 to +1. That's it. The only thing it needs to do is to calculate this Jacobian matrix, which is quite easy to do. Okay? Well, it takes a long time to do by hand calculations, but to program this, to get this matrix in the computer is quite easy to do. And to calculate then the determinant of this matrix is quite easy to do. The determinant is this times this minus this times this. Quite easy to do in a computer. 1 or 2 lines of code, you can do this. And then by doing this, you get immediately the determinant of Jacobian, and then you transform the integral in physical domain into an integral in the natural domain. The next step we are going to do in the next session is, instead of calculating this integral here analytically, we are going to calculate it numerically by using numerical integration, okay? That is another important step in finite element analysis. And I don't want to do it in this session because it becomes too long, but we will continue from this point in the next session, okay? All right, so I hope this was useful for you. I will work on the next session very soon. I hope you enjoyed, and thank you. See you.